Good evening, dear student friends. Welcome to Compiler Designs video lecture 4 on the topic SLR parsing. We know that in the last lecture we have studied in detail concept of viable prefixes and handle, which is foundation for the understanding working of any LR parser. So in today's lecture we are going to start the different SLR parsers and then we will study SLR parsing in detail. There are mainly three types of LR parsers. First one is LRK, then simple LRK, and third one is the look ahead LRK. Those are abbreviated as LRK, SLRK, LALRK. Here what is K here? K is the look ahead. Look ahead means the number of symbols we are reading from input buffer whose actual involvement will be there in taking the decision of the action in the LR parsing, that whether action has to be shift or action has to be reduce or action has to be accept or error. So this K number of symbols will be actively involved in taking the decision. So the K identifies here the number of tokens of look ahead we are reading from the input buffer. We will usually only concern ourselves with 0 or 1 token of look ahead. Normally the look ahead used is of only either 0 or 1. The reason is that if more number of look aheads will be there, it will increase the complexity of LR parser algorithm, and also it will require large memory space to store the number of states generated in the LR parsing. So to generalize, we use the K as number of look aheads. Now the different classes of parser all operate the same way. This LRK, simple LRK and LALRK, all of them they operate with the same way because they are all shift reduce parsers. They are going to take the decision of either to shift from input buffer to the stack or to reduce the handle available on top of the stack or accept if the input string is accepted, or if it is not accepted there will be error. So all these operate on the same principle, but the fundamental difference between these three is that how the parsing table is constructed. The table construction method in LRK is different as well as in SLRK is different and LALRK is different. So difference between these three parsers is in the construction of parsing table. So we will first consider LR0 parsing, which is the simplest of the LR parsing method. What do you mean by here LR0? L stands for reading the input string from left to right. R stands for using the rightmost derivation in reverse, and it uses 0 look ahead, means no look ahead is used in taking the decision of shifting or reducing in the parser. And this is also called as the weakest parser, and although of theoretical importance, it is not used much in practice because of its limitation. So because it is not using any look ahead, the parser is weak. It cannot be successfully used for all type of grammar. So LR0 parsers without using any look ahead at all. So it doesn't use any look ahead, and that's why this is LR0. Now adding just one token of look ahead to get LR1 vastly increases the parsing power. So the next category of parser is LR1. Just adding one look ahead to LR0, it increases the power of the parser, and this LR1 parser overcomes the maximum limitations of LR0 parsing. Now there are very few grammars that can be parsed with LR0 because of its limitation, but at most unambiguous context-free grammars can be parsed with LR1 compared to LR0. In fact, any language that can be parsed deterministically at all can be parsed with LR1. So any context-free grammar that can be parsed with the LR1, which can be parsed deterministically, though not all grammars for that language will be LR1. So the drawback of adding the look ahead is that the algorithm becomes somewhat complex and the parsing table gets much bigger. So this is the limitation of LR1 parsing, that just by adding one look ahead we have increased the power of the parser, but the drawback of LR1 parser is that it becomes more complex and the parsing table get much bigger because of the involvement of look ahead. So a compromise in the middle is found in the two variant of parsers SLR1 and LR1 is the LALR. So this LALR can also use one token of look ahead, but it employs technique to keep the table as small as LR0. So the advantage of LALR1 parser is that its efficiency is more than SLR1 and the table size is equal to SLR1 compared to LALR, while LALR1's parsing table size is large. So SLRK is an improvement over LR0 but much weaker than full LRK in terms of the number of grammar for which it is applicable. So normally the number of grammar that can be parsed by LR1 are the highest one, second number is LALR1 and the third one is LR0. The reason is that LR0 is the weakest parser. So LALRK parses a larger set of language than SLRK but not quite as many of LRK. So the best is efficient parser is LRK, but the reason is that the table size is large while LALRK efficiency is little less than LRK, but the table size is small equivalent to SLRK. That is the advantage of LALR. So most languages uses LALR parser in practice. So now let's start the first basic parser called as the simple LR parser. This is called as SLR parsing, simple LR parsing, or it is also called as SLR1 parsing. So this simple LR or SLR uses LR0 items, means no look ahead is used in SLR1 parsing. That's why the parser is SLR parser or simple LR parser. Now second type of parser we have just now seen is LR1 parser, which uses one look ahead. It is also called as CLR parser or canonical LR1 parser. It uses LR1 items. So there are two type of items. One is called as LR0 item, other is called as LR1 item. So LR0 item is used in LR or SLR1 parser and LR1 item is used in LR1 as well as LALR parser. So the LR parser is a shift reduced parser that makes use of a deterministic finite automata for recognizing the set of all viable prefixes available on top of the stack. This is done by reading the stack from bottom to top. So we have seen in the previous lecture with the example that how on the stack we move the input symbol from the input buffer and how viable prefixes on the stack are recognized by the DFA, also how the DFA recognizes handle which is available on top of the stack. It also determines what handle, if any, is available on top of the stack. So let's see the functioning or working of SLR parsing in detail. So what are the steps for SLR parsing? There are three important steps for understanding the working of SLR parsing. First one is that if given the grammar is there, we have to take augmented grammar or we have to modify the given grammar. How that we will see later. Second step is once the grammar is augmented, second step is create canonical collection of LR items. For SLR parsing, these LR items will be LR0 item. And then third step is drawing the deterministic finite automata or DFA and construct the parsing table. So we will see today one by one how to augment the grammar, how to create the canonical collection of LR items and how to draw the DFA and construct parsing table for SLR parsing or simple LR parsing. So this LR parser, simple LR parser uses two tables. First table is called as the action table, second table is called as go to table. The action table where action S comma A, here S stands for number of states which are rows in the parsing table and A stands for terminals of the given grammar which are the columns of the parsing table. So this action S comma A in the action table tells the parser what to do when the state on the top of the stack is S, that is the state number, and terminal A, this A is the next input available token in the input buffer. The possible actions are to shift a state on the stack or to reduce the handle on top of the stack, or third is accept the input or report the error. So because this is a shift reduce parser, there will be actions either shift or reduce or accept or error. Then second part of the table is called as the go to table. So this go to table consists of go to s comma x. Here s stands for state, which is a row of the parsing table, and x stands for non-terminals of the given grammar. So in the action table, we will be considering only terminals, that when this terminal symbol is available in the input and this state is a row index, what action is to be taken. While in the go to table, we are going to see that for state S, what is the non-terminal which is available at the top of the stack, and when this non-terminal is available, what is the state number S. So this indicates the new state to place on top of the stack after a reduction of the non-terminal X, while state S is on top of the stack. So this S will be on top of the stack, and this X will be the non-terminal which we are going to push onto the stack after reduction. So we'll see these all things with example, so you will better understand when we are going to solve a problem. So here are LR items for different LR items used for different type of parser that we have already discussed, that LR0 and SLR parser uses LR0 item, and CLR, this is also called as LR1 parser, and LALR1 parser, they uses LR1 items. So the first step just now we have seen is the for SLR parsing is augmentation of the grammar. So let's see how to augment the grammar. So given a grammar G with S as a start symbol, then we add a production S dash tends to S to the grammar. So grammar is not having first S dash as a grammar symbol, we are adding it. So whenever we have a S as a start symbol of the given grammar, we add one more production to the given grammar as S dash tends to S dot, and this is called as augmentation. We'll see what is the advantage of the augmentation. The use of augmentation helps the parser to understand when to stop parsing and announce the successful completion of parsing. So when we reduce and we reach to the start symbol of the grammar, when we add this augmented production and we reduce S by S dash, we can conclude that we have successfully parsed the input string. That is the reason why we have to augment. Now let's see what is the definition of LR0 item. An LR0 item is a production with a dot in the right hand side. So any production which is having a dot at right hand side is called as LR0 item. A bottom-up parser that starts with input string and reads symbol by symbol from left to right until a handle is detected. Once handle is found, it reduces. This is how the bottom-up parser works. It starts with the input string and reads the input string from symbol by symbol from left to right until a handle is detected on top of the stack. Once handle is detected on top of the stack, it reduces. So now let's see the definition of LR0 items. So an LR0 item of a grammar G is a production of S with a dot at some position at right hand side. So here are the examples of LR0 items. Suppose there is a production in the given grammar A tends to X, Y, Z. So it will lead to 4 different type of LR0 items. A tends to dot X, Y, Z, meaning is that the dot is at the beginning of the production, means this X, Y, Z are not read by the parser. So after the dot, X is the next symbol which the parser is going to read. The next possibility is that when X is read by the parser, dot is getting shifted at right hand side. This means that X is read by the parser and Y and Z are yet to read by the parser. Third possibility is A tends to XY dot Z. So XY means both the symbols are read by the parser and dot Z means Z is yet to read. And lastly, A tends to XYZ dot. In this case, it indicates that the whole production is read or seen by the parser and we have completed reading the production. So note that the production A tends to epsilon, if there is a production A tends to epsilon, then it will lead to one item, that is A tends to dot, because epsilon means empty string. So dot indicates the empty string in the LR0 item. So let us see an example of SLR parsing. So for understanding, we have taken a simple example. Consider the following grammar: C tends to AB, A tends to A, B tends to A. So given grammar is having 3 production. So what is the first step of SLR parsing? Augment the given grammar. So let us augment it. So how do we augment? By adding one more production above the start symbol of the grammar. So C is a start symbol of the grammar. So we are going to add one more production. C dash tends to C dot. And all other productions are as it is. C tends to AB dot, A tends to A dot, and B tends to A dot. So these are the augmentation. So when these dots will be at the end, when the parsing will be complete. In the beginning, the dots will be before this C, A, B, A and A. So once the augmentation of the grammar is over, the next step is compute the canonical collection of I0. So before this, we have to see that how to compute the closure and goto. So let's see another PPT where we will get the algorithms for construction of closure as well as goto. So let's see what are the steps to be followed for calculation of closure and calculation of goto. So we were here. An LR0 item of a grammar G is a production of G with a dot at some position of the right hand side. So these were the example of a production. A tends to XYZ. So initially dot is at the beginning, then XYZ means no production is yet read by the parser. Then A tends to X dot YZ means X is seen by the parser but YZ is yet to be seen. Next is XY is seen by the parser and Z is yet to be seen, and XYZ dot indicates that the whole production is read by the parser. And when there is a case that A tends to epsilon is there, so that will be replaced by A tends to dot in the LR0 item. Now, how do we construct? The next step is construction of LR0 items. So, how do we construct the LR0 items? So, we have got an algorithm for that. Constructing the set of LR0 items of grammar. So, here the grammar is augmented with a new start symbol. Just we have seen that what is the reason that for augmentation is when we reduce by S dash tends to S dot, we conclude that parsing is complete and successful. So, initially the C, that is the set of LR0 item, is equals to closure of the first production of the grammar. The first production of the grammar is S dash tends to dot S. So initially we compute C equals to closure of S dash tends to dot S. Now this is the start state of the DFA, that is deterministic finite automata, which recognizes the viable prefixes. Now for each set of items I that belongs to C, I is state number that belongs to C, and for each grammar symbol X that belongs to either non-terminal or terminal symbol of the grammar, such that go to I comma X is not C, means that go to I comma X should not be already available in the C, means repeat entries are to be avoided. So what we are going to see? We are going to see that from S dash tends to dot C, do we get the go-tos, that is transitions on other grammar symbols. If those are new grammar symbols, we are going to add it into the C. If not, if we are getting repeated, then we are not going to add it. And we may get some of the go-tos as empty, because not that on every grammar symbol from every state we are having a transition in the DFA. So whenever we do not have a transition on any of the states in the DFA, we will write that go to I comma x is equals to 5, that is empty, and then add the set of items go to I comma x to C. So we'll see these all things with example, then the things will be more clear. So now how do we compute the closure? Because we are going to see here that we have to compute the closure of s dash tends to dot C. So how to compute this closure? So initially we start with the closure of I equals to I, that is the state number. Then in that state, if we have a production A tends to alpha dot B beta, what is the meaning of this production? A tends to alpha dot B beta means, alpha means some of the symbols are read by the parser, and after the dot there is a non-terminal. If this type of production is there, beta means any other grammar symbols. If this type of production belongs to closure of I, then for each production B tends to gamma, means B is having another production in the grammar, B tends to gamma. Then we have to add the item B tends to dot gamma to I, if not already in I. The meaning is that in the given state we have to find a production where after the dot non-terminal is there. If after the dot non-terminal is there, we have to add that production also by adding dot at the beginning, because this is also not yet read by the parser. The thing is that it should not be a repeated entry. So we have to check that if I is not already there in I. If this is a new state, we are going to generate it. If it is repeat state, then we are not generating it. Then third step is repeat step 2 until no new items can be added. This is how to find out the closure. Now let's see the example of a closure operation. So suppose the given grammar to us is E tends to E plus T or T, T tends to T into F or F, F tends to E enclosing the bracket, and F tends to ID. Suppose this is the productions we are given to us. So how do we compute the closure of E dash? So first step is augmentation of the grammar. So start symbol is E. So we augment it by E dash tends to dot E. So how do we compute the closure of E dash tends to dot E? See here. The first step will be E dash tends to dot E. Now after the dot there is a non-terminal. So what does the closure rule says? The closure rule says that after the dot, if there is a non-terminal, then you have to add its production. So here after the dot B was there, so we added B tends to gamma into closure of I. So here also after the dot non-terminal is there, capital E is a non-terminal. So we are going to add E production. So see here what are the E productions in the given grammar? E tends to E plus T and E tends to T. So we are adding these two productions with dot at the beginning. So E dash tends to dot E is the first step for production of the grammar. After the dot E is a non-terminal. So we are adding E productions. E tends to dot E plus T, and another production is E tends to T. So E tends to dot T. So now here E productions we have added. Now see here after the dot again T is there. T is also a non-terminal. So add its production. So in the next step E dash tends to dot E, E tends to dot E plus T, E tends to dot T, and because T is a non-terminal, add T productions. What are the T productions? T tends to T into F or T tends to F. So we are going to add T tends to dot T into F and T tends to dot F. Now again F is also a non-terminal. So we are going to add F productions also. So E dash tends to dot E, E tends to T, E plus T, E tends to dot T, T tends to dot T into F, T tends to F as usual from the previous step. And then because after the dot F is a non-terminal, we are going to add its productions also. That is F tends to dot E enclosing the bracket and F tends to dot ID. So this is the whole closure of E dash tends to dot E. This is how do we compute the product closure of any production. Now how to compute the goto? Goto will tell us that from any given state where does the transitions go in the DFA. So what is the steps to compute the goto operation? For each item A tends to alpha dot x beta belonging to any state I. What is the meaning of this rule? that alpha is some grammar symbols, those are available before dot, and after the dot there is x, means a non-terminal is there, or x is a terminal also. Capital X stands for terminal as well as non-terminal symbol of the given grammar. So after that any symbol is there, we are adding the set of items into the closure as A tends to alpha x dot beta. Means what we take a transition in the DFA. So when we take a transition in the DFA, this dot gets shifted to the next symbol. So add the next item as closure of A tends to alpha x dot beta. That means that x is read by the parser, and take a transition in the DFA, go to I comma x. Just see that if this type of production is already not there in I, if it is already there, then don't add it repeatedly. If it is a new, then only we have to add it. So repeat step 1 until no more items can be added into the go to I comma x. So we have to repeat this for all the symbols of the grammar, maybe terminal symbols, maybe non-terminal symbols. Then intuitively, go to I comma x is the set of items that are valid for the viable prefix gamma x, when I is the set of items that are valid for gamma. So this is nothing but how do we compute the go to. So let's see an example of go to operation. Suppose the closure of I just now we have computed is this: I equals to E dash tends to dot E, E tends to dot E plus T, E tends to dot T, T tends to dot T into F, T tends to dot F, F tends to dot E enclosed in the bracket, and F tends to dot IV. So how do we compute the go to of this I? After the dot, whatever symbols are there on that we are going to take in the transition in the DFA. So go to I comma E. E is one of the grammar symbol. So how do we compute go to I comma E? We compute it computing the closure. So closure of E dash tends to dot E. So when we take a closure and go to, this dot will get shifted to the next symbol. So closure of E dash tends to E dot. Then there is one more production where before the dot, the dot is before E. So here also dot has to be shifted because we are reading E. So if we are shifting dot of this after E, here also you have to shift dot of this E. So closure of go to I comma E is equals to E dash tends to E dot comma E tends to E dot plus T. Now here plus is a terminal, so we cannot take closure. If this would have been a non-terminal, we have to add its production as well while computing the closure. So closure of the go to I comma E is nothing but E dash tends to E dot and E tends to E dot plus T. This is how we compute the go to I comma E. Similarly, we can compute go to I comma T. It will go on both of these, then I comma F, then I comma opening bracket I comma ID. This is how we compute the go to for all the grammar symbols. So this is the one more example of go to operation. Suppose in the given state I, we have production E dash tends to E dot and E tends to E dot plus T, the previous step. This. Now how we can extend further go to here? When we compute go to on I comma plus, because after the dot here plus symbol is there. Here nothing is there, so we cannot go ahead. But here dot can be shifted after plus when the parser reads plus. So go to I comma plus is equals to closure of E tends to E plus, here dot is getting shifted dot T. Now as I told just now, after the dot, if non-terminal is there in the closure, we have to take its productions also. So we are going to add it. E tends to E plus dot T, T tends to dot T, because T is non-terminal, we have to take its productions. T productions are T tends to T into F or F. So T tends to dot T into F, then T tends to dot F. Now here again F is non-terminal after the dot, so we have to add its productions. So F tends to dot E enclosing the bracket, and F tends to dot ID. This is how we compute the goto on I comma. This we have seen that how the algorithm for computation of closure and computation of goto works. Now let's come to our example. Now here we will be needing these two algorithms to compute the closure of and goto of the given productions. So second step is once we augment the grammar and we have to give the number to the grammar productions. This is the first production, this is the second production, this is the third production, this is the fourth production. So once we augment the grammar, next step is compute the canonical collection using closure. Okay. So initially the I0 is the first state of the DFA. So which computes the closure of C dash tends to dot C, because this is the first production. C dash tends to dot, actually it should be C dash tends to dot C, this should be C tends to dot AB, this should be A tends to dot A, and here this should be B tends to dot A. By mistake here dots are placed at the end, those should be at the beginning of the production, which indicate that we have not yet seen or read any production by the parser. So closure of C is C dash tends to dot C. Now after the dot, C is a non-terminal. So we have to add C productions. So what are the C productions in the grammar? C tends to dot AB. So add C tends to dot AB. Now after the dot again there is a non-terminal A. So we have to add A production. What is A production is? Dot A. So A tends to dot A. See, let me change this slide to avoid your confusion.